Previously, you will have learned about nuclear decay and half-life, and if not, I want you to go back and have a look at my lesson videos from GCSE Physics so you understand the definitions correctly. For A-level, we're going to be focusing more on the decay curve, looking at the equations for it and understanding what the decay constant is. But first off, we need to understand some key definitions. So let's have a look at those to start off with. The words we're going to cover are decay, spontaneous, random, activity, half-life, and the decay constant. So let's start off. We'll start with decay. Decay is the process by which a nucleus of an unstable atom loses energy by emitting ionizing radiation. So the nucleus is unstable, meaning we are not talking about bombarding nuclei like in a reactor. Also, energy is emitted as ionizing radiation. So it's not any nuclear reaction. Fusion and fission do not emit ionizing radiation, so they are not decay. We typically think of decay as being that thing that happens when alpha, beta, or gamma are emitted. Spontaneous. As said, decay is happening in unstable nuclei, and so it will just happen. Sometime, or never. Spontaneous means that the decay is not affected by external factors. If we heat up the radioisotope, the decay rate stays constant. Cool it down, no change. Hit it, no change. Crush it under high pressure, no change. Put it next to lots of other decaying nuclei and still no change. Spontaneous means it can happen, but we can't control when. Now this is a problem because if we can't control it, the best we can do is contain it, making nuclear waste an environmental headache. Random is, well, it's difficult. Humans are not very good with random. Our brains don't really understand it unless we try hard. If I write a string of numbers on the page here, and another one over here, which one honestly looks more random to you? Now, answering this genuinely, most people would say the first one. The numbers don't repeat, there's no runs, etc., etc. But really, if it's random, each position in the string of numbers has equal chance of being 0 to 9. This 5 here should not be influenced by whether the number next to it is a 4, a 6, or a 2. It should be random. So, humans, anyway, are generally bad at recognizing randomness. Our definition is going to be that since nuclear decay is random, we cannot predict the time for an individual nucleus decay, and all nuclei have equal probability of decay. Since we couldn't actually really judge randomness, let's stick to a clear definition. Activity. Now this one's simple. The activity of a radioactive sample is the rate at which nuclei decay. So it's the number per second. The half-life has two definitions. The first is that it is the mean time taken for half of the active nuclei in a sample to decay. The mean time taken for half of the active nuclei in a sample to decay. You'll have seen the curve before, the decay curve. As time continues, the number of undecayed nuclei drops. Each half-life, T-half, the number reduces to half of its previous value. This line has an equation n equals n0 e to the minus lambda t. The current number of undecayed nuclei is equal to the original number n0 multiplied by e to the minus lambda t, where t is the time and lambda is a constant, called the decay constant. We'll get to that later. Each unit of time, there is activity, decay, and obviously this depends on how many radioactive nuclei are present. If there are more of them, there's more chance that more will decay and emit ionizing radiation. So we could just as easily change the y-axis to activity, A, and change the formula to A equals A0 e to the minus lambda t. And that brings us to the tricky one, the decay constant. It's defined as the probability that an individual nucleus will decay per unit time. And that's a good place for a recap. Decay, that's the process by which unstable nuclei release energy in the form of ionizing radiation. Spontaneous means that we cannot control what is happening. The decay is not affected by external factors. Random means we cannot predict the time for an individual nucleus to decay, and all nuclei have equal probability of decay. Activity is the rate of decay. Half-life is the time taken for half of the radioactive nuclei to decay, or the time for the activity to reduce to half of its original value. And the decay constant is the probability that an individual nucleus will decay per unit time. Back to the decay constant. It shouldn't really be too tricky. All it is the constant of proportionality between A and N. So A equals lambda N. Let's see why. The total number of nuclei that decay must be equal to the probability of one nucleus decaying multiplied by the total number of nuclei. If I have 50 nuclei and each nucleus has a 20% chance of decaying, then on average I'd have 20 over 100 times 50 equals 10 nuclei decaying. 20% of them decayed. So let's change it to saying that the total number of nuclei that decay per unit time must be equal to the probability of one decaying per unit time multiplied by the total number of nuclei. In other words, or letters, A equals lambda N. The name decay constant and the fact that it is a probability causes some confusion, but the maths is there. Okay, let's finish off by relating everything to the half-life. Starting with the decay curve equation, n equals n0 e to the minus lambda t. We're going to say that when time t equals t half, n drops to half its original value, which was n0. So, rewriting the equation, let's substitute t half for t, and n0 over 2, half of the original number of radioactive nuclei, substitutes in for n. n0 over 2 equals n0 e to the minus lambda t half. Now we have n0 on both sides, so we can divide that out. Half equals e to the minus lambda t half. Take natural logs of both sides. ln1 over 2 equals minus lambda t half. And with ln1 over 2 equal to ln1 minus ln2, that equals 0 minus ln2. So we get minus ln2 equals minus lambda t half. ln2 equals lambda t half. Let's rearrange that so that lambda equals ln2 over T half. And this handy equation gives a nice simple link between the decay constant and half-life. So at the end we have some definitions for the key terms. We've got equations for the decay curve, and we've got a couple of different ways of thinking about the decay constant. The decay constant itself is really important because it gives us a handy way to calculate the half-life, but it can cause some difficulties because of the different ways we think about it. It comes up in the decay curve, we've got that way to calculate the half-life, but at its heart it is the constant of proportionality between activity and n, the number of radioactive nuclei. So look through the maths and look to see how the things are related through mathematical terms.